Welcome to another new video of interesting math problem on our channel Math Solutions for You. Please do like, share, comment, and don't forget to subscribe to our channel. In this video, instead of starting with a problem, I'm starting with what I think is one of the most elegant theorems in plane geometry, and I'd say in mathematics in general. And that's Pythagoras Theorem. And this is something that's very, very important for any high school math tests or any standardized tests. So what does the Pythagoras Theorem state? It states that in a right-angled triangle, the sum of the squares of the two shorter sides is equal to the square of the hypotenuse. And it's a very, very simple relationship, but it's not as intuitive as one might think it is. And today, for the first part, I'll focus on the proof of this theorem, because that's something that was of interest to me recently. And I did look up the internet for videos or other statements of proof of the Pythagoras theorem, and most of the proofs that I came across involved constructions of squares in different ways, taking lengths of the two triangles and then lengths of the two sides of the triangle rather, and then completing some squares. And while those proofs may be intuitive to some, to me, those constructions always appeared very complicated. And while they are kind of easy to understand once you know what to construct and how to proceed, it's always so difficult to remember, so that if someone asks later, do you know or do you remember how that proof was done, you always have to go back and then look up the reference of where you read the proof, or look up the videos. In my case, I was looking through YouTube videos. So to remember to be able to do those constructions that leads to the correct proof. So one of the ways, and I find it a much easier way to prove the Pythagoras theorem, is by similarity of triangles. And that's a proof that's not particularly common, at least based on my experience looking this up on the internet. But it's something that's much, much easier, in my opinion, to remember and to relate to, rather than the completing different constructions of squares in different ways, which is a fun way, agreeably, but not always something that you can easily reproduce. So this particular method that I'm going to show you is going to rely on only one simple construction. So I'm going to show you, but let's start with a simple triangle. So this is a right angle triangle, and angle ACB is 90 degrees in this case, and the lengths of BC, AC, and AB are A, B, and C respectively. And angle ABC, let's call this angle theta, which makes the other angle of the right angle triangle, which is angle BAC, as 90 degree minus theta. Now the construction in this case, like I said, this particular proof doesn't involve constructing squares or anything of the sort. The only one construction that you need is drop a perpendicular from the vertex C onto the hypotenuse. And let's call this perpendicular as CP. And let's denote the length of CP by small p. So considering triangle ABC, the area of triangle ABC, if you regard AC as the base of the triangle, we know that area of the triangle is half base into altitude, half base multiplied by altitude. So base is AC, the altitude will be BC, because BC is perpendicular to AC, angle ACB being a 90 degree. So that's quite obvious. So one way of writing the area of triangle ABC is simply half A multiplied by B, where small a is the length of BC and small b is the length of AC. Now if you consider, instead of taking AC as the base, you can pretty well turn the triangle around and consider AB as the base, the hypotenuse AB as the base. And if that's the case, then the altitude of the triangle will be simply CP, right? And we have denoted the length of CP as small p. So considering the hypotenuse as the base, the area of triangle ABC comes to half P multiplied by C. But it's still the area of the same triangle, right? So we can equate these two quantities. Half AB is equal to half PC. And from that, we get AB is equal to PC, from which it's simple to obtain P in terms of AB and C. So P, remember, small p is the length of the perpendicular CP from the vertex C onto the hypotenuse AB. So now let's look at what these angles are. So we have two triangles that are formed, triangle BPC and triangle APC. And what is the value of angle BCP? Well, we know that BCP is a right angle triangle, angle BPC being 90 degree, right? So perpendicular. So the sum of the other two angles, namely angle PBC and angle BCP, must add up to 90. And since PBC is indicated as theta, then BCP must be 90 minus theta. And similarly, the other angle should then be simply theta, because those two again should add up to 90, because angle ACB is 90 degree. So the other angle PCA or angle ACP, however you want to call it, that should be theta. So now consider the triangles BPC and ACP. Their angles are all similar or are the same. The corresponding angles are same as that of the original triangle ACB, or ABC, which makes all of those three triangles, the big triangle, the original triangle, and the smaller two triangles, similar to each other. Now let's indicate the length of BP by small x and length of PA or AP by small y. So from similarity of the triangle ABC and triangle CBP, we basically have x by p is equal to a by b. So x is the shorter of those two arms of the right angle triangle, right? In triangle CBP, right? And P is the longer of the two arms of the right angle triangle CBP. So if we look at the original triangle ABC, the corresponding arms would be A and B. The short arm is A and the long arm is B. So that's why we have x by P is equal to A by B. And from this we have x equal to PA by B. And if we substitute P equal to AB by C, which is what we arrived at previously from equating the two areas, right? Equating the areas, half AB equal to half BC. Then if we substitute P equal to AB by C, we get x is equal to A squared by C. And similarly, from similarity of triangle ABC and triangle ACP, we can write y by P is equal to B by A. And from this we obtain y is equal to PB by A. And again we substitute P is equal to AB by C, we get B squared by C. And now if we simply add up x plus y, that becomes C. But we have already expressed x as S squared by C and y as B squared by C. So we can substitute that for x and y. We have A squared by c plus b squared by c is equal to c. And then you multiply both sides by c and you get s squared plus b squared equal to c squared, which completes the proof of Pythagoras theorem. So this is a proof that does involve knowledge of similarity of triangles, but it's a very simple one to remember in terms of what constructions you need to do. It's a simple construction. You just need to drop a perpendicular from the right angle onto the hypotenuse, from the right angle vertex onto the hypotenuse, and that's it. So the reason I did this proof is I also wanted to, show some of the important results, because this is a very common topic in standardized test. And I'll show you one of the GRE quantitative comparison problem here next, which doesn't really need you to prove the Pythagoras theorem, but the results of similarity that we obtain will make this problem very, very easy. So this is basically, the problem of a right angle triangle. Angle ACB is 90. AC is given as 8. BC is given as 6. CP is the perpendicular from C to hypotenuse AB, and BP is given as X. And you are asked to compare two quantities. The quantity A is 2x and quantity B is 6. So if you remember the results that we obtain from similarity of triangles, because whenever you have this case of a perpendicular being dropped from the right angle vertex onto the hypotenuse, the triangles that you get are all similar. So let's call the side BC as A, side AC as a B, and then side BA or AB as C, and let's call the other part, so BP is given as X, let's call the other part Y. So this is kind of consistent nomenclature with the proof that I showed previously. So we know that X is equal to A squared by C from the previous proof. And in this case, C is not given, but we can apply Pythagoras theorem. Like I said, we don't need to prove Pythagoras theorem here. We can just take the result. C squared is equal to A squared plus B squared, and that makes C squared is 100, which makes C equal to 10. And now we know A, C, we can find X by simply plugging in the value. X equal to A squared by C equal to 6 squared by 10, that makes it 3.6. And that will make 2x equal to 7.2, which is greater than 6. So the correct answer will be quantity A is greater. So remembering, these relationships basically allows you to solve this problem in a minute or even less than a minute.